Yeah, so thanks very much for the invitation to speak. So this is some joint work with Sondre Kvamme. And since it's a short talk, I'm just going to tell a very short story. K will be a field, and I'll consider a finite dimensional K algebra lambda, and ask you to recall that such an algebra is Gorenstein if its injective dimensions as a left module over itself and as a right module over itself are both finite, in which case they coincide. And I'll call this at most D Gorenstein if that finite number is at most D. And if I have an algebra lambda with this property, then a natural category to consider is that of Gorenstein projective, or sometimes maximal Cohen-Macaulay lambda modules, which are those finite dimensional lambda modules with no positive extensions on lambda. So a kind of prototypical example here would be if lambda is self-injective, then the number D can be taken to be 0, and this is the whole module category. And in general, it's some Frobenius subcategory of that. And it's functorially finite in the module category, and that means it has almost split sequences. And so it has an Auslander Reiten translation, which I'll call tau GP. And the thing I want to point out is that this is not the same as what you, as restricting the Auslander Reiten translation tau lambda on the whole module category to this subcategory. And tau lambda does not preserve Gorenstein projectivity in general. So the upshot is if I take some Gorenstein projective lambda module, I have two ways of taking its Auslander Reiten translation, either by forgetting it was Gorenstein projective and just applying the ordinary one, or by taking this translation in the subcategory. And the question I want to ask is how these two translations are related. So to answer that question, I need a little bit of notation. So for a module M, I'll denote by omega M its syzygy. So this is a kind of standard piece of notation. So I take a projective cover of M and I take its kernel, and I'll call that omega M. And the other slightly less standard thing to do is I can take a left approximation by projectives, which is a little bit odd. I can do that. And I can take its co-kernel, and I'll call that sigma of M. And then I obtain an adjoint pair of functors. Sigma is left adjoint to omega as functors on the stable module category of lambda, i.e. mod lambda modulo projectives. And so then the theorem is that if lambda is at most D when over Gorenstein, then what happens, I have my two Auslander Reiten translations. I can post-compose them with the dth power of the syzygy, and then they become equivalent as functors on the stable category of Gorenstein projectives. Okay. So I'm going to even try and give you a proof of this. And that works as follows. So let me consider morphisms of stable morphisms up to projectives, stable morphisms, into omega t tau lambda of x for some Gorenstein projective x. Well, the first thing I can do is apply adjunction to turn the omega into a sigma. And then I can apply the Auslander Reiten formula to get the dual of x1, x2 sigma d of black. Yeah. And if I do the same thing, but I instead start with tau GP in place of tau lambda, then, well, okay, again, I apply adjunction, and then I apply the Auslander Reiten formula, and again, I end up with dx1 sigma d. So these two things are equal, and hence the two things I started with are also equal. And so then by Jornada's lemma, these two syzygies or syzygies of the translations are isomorphic. Okay, and every equality I wrote down is coming from a natural transformation of functors. So this isomorphism is natural in X. Okay, so if that seemed very slick, then there is one little detail, which was this equality here. I was a bit slick a bit. This uses a lemma that you have to prove, which is that the dth power of sigma takes values in Gorenstein projectives. So that's true and needs a proof, and that's what allows you to actually apply the Auslander, the relative Auslander-Reiten formula on the subcategory at that point. This is quite well known for omega d, but not so well known for sigma d. Okay, so this is it's a relatively easy observation once you know you need to make it, and it can be deduced in other ways for it. I mean, for example, from work of Auslander and Reiten, at least at the level of this isomorphism here, which we upgrade to a natural transformation of functors. So when we were thinking about this, we had a particular aim in mind, which was an application to, sorry, let me try and leave the theorem on the screen, which was an application to some results about Calabi properties, appearing in some work of Garcia Elsener, some of it with Ralph Schiffler. The stable category of Gorenstein projective lambda modules is it's always a triangulated category. It's d plus 1 Calabi if this dth syzygy of tau gp, if that functor is the identity or naturally isomorphic to the identity. And so that fact, together with our theorem, gives a new proof of a result of Garcia Elsener and Schiffler, which is that if lambda is a 2 Calabi tilted algebra, then a module for it is Gorenstein projective if and only if it's fixed by omega squared tau lambda. Maybe just to point out, sorry, I need to say something else first. So how do we deduce this from our result? Well, we use some other work by Keller and Reiten, which says, firstly, that an algebra lambda in this class, 2 Calabi tilted algebra lambda, is one Iwanaga Gorenstein. So our result applies. And one consequence of that is that this omega squared tau lambda of m certainly is Gorenstein projective. So the more difficult direction in this theorem is to prove that each Gorenstein projective module satisfies this isomorphism. So that's what we can really do. Well, then our theorem says I could replace this tau lambda by tau gp, and Keller-Reiten also tell me that this stable category of Gorenstein projectives is 3 Calabi. So in fact, as soon as you can replace this tau lambda by tau gp, this becomes clear, taking Keller-Reiten's result as given. And so then the second corollary, very quickly, is that if the field is algebraically closed and lambda is an M cluster tilted algebra of type A or A tilde, then we can conclude that this stable category of Gorenstein projectives is M plus 1 Calabi. And now we use a result of Garcia Elsener, who proves that firstly lambda is Iwanaga Gorenstein, the dimension is opposed to M, and gives another of these kind of fixed point theorems. So a module is Gorenstein projective if and only if it's fixed now by omega M tau lambda M. Okay, so our theorem says, well, I can replace this tau lambda by a tau gp. So so it looks like omega m tau GP is going to be isomorphic to the identity. So that's at least true on the level of objects. You want that isomorphism to be natural in M, but these algebras are very, very special. They're gentle algebras. And so that means that this stable category of Gorenstein projectives is semi-simple. So it's not very difficult to construct a natural isomorphism of functors just from a bunch of isomorphisms after evaluation on each object. Okay, I think I'm out of time, so that's where I should stop.